This is part 2 of the AQA A-Level Chemistry topic, Nomenclature and Isomerism, Year 13. In part 1, we looked at some of the key IUPAT rules for naming compounds. In this one, we're going to revisit some of the forms of isomerism you know and introduce a new one. So I'm going to recommend that you pause as you go, have a go at every activity as you're working through. So let's start off with the objectives. I can describe what type of molecules show optical isomerism. But before then, as I've said, we're going to revisit the work you did in Year 12. So have a go at recalling the definition for structural isomerism. This will be a 2-mark question in the exam. And for structural isomerism, it's the fact that species have the same molecular formula, but a different structural formula. But there are 3 types of structural isomerism, so let's look at each of those. Give an example in each case where you can, and I'll share some examples as well as we go through. So for chain isomerism, it's the same molecular formula, the same as we said for structural, but specifically we've got to say what the difference with the structure is. It's a different arrangement of the carbon chain. Now, the example that I'm going to give here is if I take butane and methylpropane, they are both C4H10. Let's take a look at positional isomerism now. So, you're seeing a theme here, hopefully, same but different. In this case, it's the same molecular formula again, but it's a different position of the functional group. It's a very important distinction you're going to have to make as we move through to the next definition as well. The example that I'm giving here, I've got propan 1-ol and propan 2-ol. And they both have the formula C3H7OH, same molecular formula, but my alcohol group is in a different position on the carbon chain. Finally, functional group isomerism. 3rd type of structural isomerism. So once again, the same molecular formula, but this time a different functional group. Now, there's actually 3 key functional group isomers that you will need to remember the pairings of that come up very, very commonly. So I'm going to show you examples of each of them. First one is alkenes and cycloalkanes. You can see here I've drawn butanene and cyclobutane. The next one that you come across is aldehydes and ketones. They almost look positional, but remember, if the double bond O is on the end of a carbon chain, it's an aldehyde. On the middle of the carbon chain, it's a ketone. And the final one that you'll see a lot more in the carbonyl topic in Year 13 is esters and carboxylic acids. So I've got here butanoic acid, the acid at the top, and ethyl ethanoate, which has the same molecular formula, which is an ester, down at the bottom. So have a think then about geometrical isomers that you learnt about in Year 12. The first part of the definition here is they have the same structural formula. Not the same molecular formula, it's more than that. Their structural formula is the same. You need to remember that their arrangement in space or spatial arrangement is the key difference. Now, I'm going to use an example here that comes up very, very commonly. I'm going to look at but2ene. And you can see that they both have the formula CH3, CH, CH, CH3. I could write it out as a structural formula. But on the first one, on the left, I have got one CH3 below the double bond, one above. And in the second example, they are both above. Now, E stands for entgegen, so that's E-but2ene on the left and Z-but2ene on the right. The full details of this are included in the Year 12 isomerism playlists, and I really recommend you go back and look at those if you need to refamiliarise yourself with them. But in terms of how you can determine whether something shows geometrical isomerism, it's not the most scientific way, but I tend to go through the 3-tick rule. If we take a look at E-but2ene on the left, we know it has geometrical isomers, so we know it's going to satisfy the criteria of all 3 rules. But rule 1, is there a double bond? If there's a double bond, then absolutely there could be geometrical isomerism. What we then need to do is look at each carbon in the double bond. Does the carbon on the left of the double bond have 2 different groups connected to it? If so, that's a second tick. Finally, does the carbon on the right of the double bond have two different groups connected to it? Absolutely, it's a tick. The carbon on the left has an H and a CH3. The carbon on the right has an H and a CH3. That's 3 ticks, and that tells me that but2-ene exhibits geometrical isomerism. Okay, so we're going to move on to optical isomerism. In this case, it's another type of stereoisomerism, but it's the same definition, the same structural formula, but a different arrangement in space. The first question here is actually about careless errors in nomenclature. What should chloro, bromo, methyl, iodo, methane be called? Well, the first thing you notice when you draw it is there's actually a carbon chain of 2, so the name is based on ethane. The rest of it is about remembering that prefixes go in alphabetical order. So it would be bromo, that's the wrong way around. It would be bromo, chloro, iodo, ethane. But more than that, all of those halogens are on the first carbon. So it's 1 bromo, 1 chloro, 1 iodo, ethane. We're going to draw that out now in a tetrahedral structure. So what would an alternative version of this look like that has a different arrangement in space? Well, the key here is that you draw your mirror line. I would always draw the mirror line in and then draw my reflected image. Because what you've now got are 2 isomers with the same structural formula, but they are actually not superimposable. And I hope you've had a chance to actually build these in the lab when you've been studying to actually see that they're not superimposable. Have a go at bromochlorofluoromethane. What do we think they are going to look like? Well, bromochlorofluoromethane is going to look like this. I can draw my mirror image, which gives me this. And you can see that they are mirror images of each other. My chloros are on opposite sides. My fluoros are both going down. My bromos are both going up. My H's are going in towards the mirror. They are not superimposable. So, mirror images is the key takeaway that I want you to take from optical isomerism. That's the easiest way to draw them. Now, this topic also introduces a lot of new key terms. Enantiomers. The 2 optical isomers are called enantiomers of each other. To have an optical isomer, you have to have a carbon in the centre with 4 different groups coming from it. That makes that carbon asymmetric and it makes it a chiral centre. So we've got all of these key terms that you need to be familiar with. So where would the chiral centre be on this structure, and what would you name it? Well, this can be tricky when you look at it at first glance because it is a skeletal formula, but there is an H coming off the carbon that I've asterisked as well. So I've got 4 different groups coming off: a CH3, an NH2, a COOH, and an H. My longest carbon chain here is propan. There is a COOH on the end, which makes it propanoic acid, and I've got an amine group on the second carbon, so it's 2-amino-propanoic acid. Have a go at drawing out the tetrahedral structure of 2-amino-propanoic acid, and then see if you can do the mirror image of it as well. So this is showing exactly the same structure, but it's drawn in a way that makes it easier to see the chiral centre, and it makes it easier to show the mirror image, as I have done here. So we've gone through all of that. What do we think are going to be the significant differences in chemical properties and physical properties of optical isomers, of enantiomers of each other? Optical isomers of the same compound. Well, the chemical properties are identical. Their physical properties are also identical. So it begs the question why this is so important. And we're going to touch on that a little bit more on the next video, but we're now going to focus on how we can recognize different optical isomers, because there is something that they do differently. They show different optical activity. One optical isomer will rotate plane polarized light in one direction and one will rotate it in another. So if I polarize light, so I only have it in a single plane, as we can see here, one isomer will rotate it, as I've said, in one direction and one will rotate it in the other. And we would say that one will rotate clockwise and one will rotate anti-clockwise. And you can use a polarimeter to actually measure the rotation of the plane of polarization. So I take my light, I shine it through a Polaroid, which gives me plane polarized light. That plane polarized light is then passed through my sample, and then you simply measure the angle of rotation. So it's good to have an awareness of how we measure it, but it's really important that you remember the key difference between them, and that is their effect on the rotation of plane polarized light. That takes us to the end of this video. Thank you for listening and goodbye.